Hello students, from past few classes we are studying metric spaces, and particularly in the last class we have revised the definition of metric and metric spaces, and also we have studied three illustrative examples to clarify the concept of metric and metric spaces. Now in the today's class also we will study some more illustrative examples. So to begin with is the example number 4. As told earlier, illustrative examples means these examples are just for the understanding purpose. Okay. So the example number 4 is, let L infinity denote the set of all bounded sequences and series that we have studied in the semester 3rd of BSc second year. Okay, so let L infinity denote the set of all bounded sequence Xn of real numbers. With the function d, defined as how the function d is defined in this case. It is defined as a d of sequence Xn, sequence Yn. Okay, it is equal to the supremum, in short SUP, supremum of the set of all absolute values Xn minus Yn, where n ranges over the set capital N of natural numbers. Okay, and this is for every sequence Xn, sequence Yn belongs to L infinity. Okay, so this one. Then this one L infinity. This one is a metric space. Okay, on L infinity is a metric space with the d as the metric. So therefore we can say that L infinity, d is a metric space. This is a metric space. So obviously, as told earlier, first three conditions can be verified orally also. So here we'll prove only the fourth condition. Okay, we'll check only the triangle inequality, which is the most important condition. It is the condition number 4, because the first three can be verified very easily. Okay, so solution of this. Let sequence Xn, sequence Yn and sequence Zn be any three bounded sequences of real numbers. Okay, be any three bounded sequences of real numbers means those are the members of L infinity. Here L infinity denotes the set of all bounded sequences of real numbers. Okay, so we have taken three members from this L infinity set, and those are the sequence Xn, sequence Yn and sequence Zn. Okay, and d is defined, which is its definition is given in the question itself. So it is this. So if we have to check the first condition, then we know that the distance between sequence Xn and sequence Yn, which is defined here, is the supremum of this set, and this set is the set of non-negative real numbers. Okay, so and we know that the supremum of the set of non-negative real numbers is obviously non-negative. Therefore this quantity, distance between sequence Xn and sequence Yn, will be always greater than equal to 0. Therefore the first condition verifies here. Second condition is the coincidence. We know that the distance between sequence Xn and sequence Yn will be equal to 0 if and only if this right hand side means the supremum of these non-negative numbers is 0. And we know that the supremum of non-negative numbers will be 0 only when each and every member is 0. So therefore we'll get each and every mod xn minus yn equal to 0, and which implies that each xn will be equal to corresponding yn, which means that x1 equal to y1, x2 equal to y2, and so on, and which means that in that case sequence xn and sequence yn will be one and the same sequences. Okay. Next, number 3 is the symmetry. We have the distance between sequence xn and sequence yn is equal to supremum of the set of modulus of xn minus yn. Okay, and we know that the mod of xn minus yn is same as the mod of yn minus xn, and therefore supremum will be also the same, and therefore the distance between sequence xn and sequence yn will be same as the distance between sequence yn and sequence xn. Therefore, in such a way, three conditions can be very easily verified, and without those we have checked orally also. Okay. Now we'll move to the fourth one, that is the triangle inequality. And for proving the triangle inequality, we have considered three members from the set L infinity, and those three members are sequence xn, sequence yn, and sequence zn. Okay. So this one. So therefore we will begin with the left hand side of that one. So we have distance between sequence xn and sequence yn. Okay, this is equal to, use the definition of the d function of this example. So it is equal to the, by the definition, this is equal to the supremum of set of mod of xn minus yn, where n ranges over n. Okay, now which is same as supremum of mod of xn minus zn plus zn minus yn. Okay, and this is again for every n belongs to n. We have subtracted and added a real number. Here zn is a real number, and adding and subtracting the same real number means adding 0, and addition of 0 doesn't makes any change. Okay, as we have seen in the first illustrative example in the last class also. So now we'll make groups in such a way. The first group will make of the xn minus zn, and second will make of the zn minus yn. Okay, now this is less than equal to supremum of the set of mod of xn minus zn plus mod of zn minus yn. Why it is so? That I have explained in the first illustrative example in the last class. Okay, we have what we have mod of a plus b is less than equal to mod a plus mod b. So this property of the absolute value function we have used once again here. Okay, so therefore we got less than equal to. Now this is equal to supremum of, as mod of xn minus zn is a non-negative quantity, as well as mod of zn minus yn is a non-negative quantity. So therefore we can separate this, and it can be written as this is equal to supremum of mod of xn minus zn, where n ranges over capital N. Okay, and plus supremum of mod of zn minus yn, where n ranges over capital N. Capital N is the set of natural numbers. And again, by the definition of d function, the first one quantity, okay, is nothing but it is the d of xn comma zn. So this first one quantity is this much, is nothing but it is the d of sequence xn comma sequence Zn, and plus the second quantity, this one quantity by the definition of D function is nothing but it is D of sequence Zn comma sequence Yn. Okay, so like such we have this, and finally this is nothing but what we have shown. So therefore we have shown that the distance between sequence Xn and sequence Yn is less than equal to the distance between sequence Xn and sequence Zn plus sequence Zn and sequence Yn. So therefore in this way we have shown that the triangle inequality holds. Therefore the triangle inequality holds, and therefore D is a metric. Therefore D is a metric on X. Here X means L infinity. So therefore D is a metric on X, and hence L infinity comma D is a metric space. This is a metric space. Okay, this metric space is also called as a supremum metric on L infinity. This is a supremum metric on L infinity. So this was the fourth example. Now next one we will move to the next example, which is the fifth example. Example number 5. If we consider the set capital C, closed interval 0 to 1. Here capital C is for the continuous functions. Okay, the set capital C, closed interval 0 to 1, which consisting of all real valued continuous functions, all real valued continuous functions defined on closed interval 0 to 1. Okay, with the function D defined as D of f comma g is equal to, it is the integration from 0 to 1 of mod of fx minus gx, okay, dx, and this is for every pair of functions f comma g belongs to C closed interval 0 to 1, C 0 to 1. Then this C closed interval 0 to 1 with the function D defined as such is a metric space. Okay, it is a metric space. So see here, if we consider the set of all continuous real valued functions defined on the closed interval 0 to 1, set of all continuous real valued functions defined on closed interval 0 to 1 means whose domain is closed interval 0 to 1. If we take the set of all such continuous real valued functions and suppose it is denoted by C closed interval 0 to 1, then on that set if we define the function D as D of f comma g, now obviously C is the set of all continuous functions defined on closed interval 0 to 1, therefore members of this set C are some functions, okay, which are continuous on closed interval 0 to 1 and they are real valued functions. So D function is defined as D of f comma g is equal to the integration from 0 to 1 mod of fx minus gx dx. This is for all f comma g belongs to C closed interval 0 to 1. Then in this case also we can check that This D is a metric on this set, and therefore C closed interval 0 to 1 along with the metric D is a metric space. Okay, so this is a metric space, and this metric space which is defined here is for the continuous functions. Next one, example number 6. As these are just illustrative examples and we have solved first 4 examples in so much detail, therefore we are studying these remaining 3 examples in little bit short. Next one, example number 6. Suppose if we consider the set C, okay, same set C. So let C closed interval 0 to 1 be the set of all continuous real valued functions defined on closed interval 0 to 1, and let us suppose that the function D, okay, function D is defined by D of f comma g, which is equal to supremum over x belongs to closed interval 0 to 1. Means here x can be any one member from the set closed interval 0 to 1, but supremum of fx minus gx. Okay, supremum of fx minus gx, and this is for every pair of functions f comma g belongs to C closed interval 0 to 1. So if the function D is defined in such a way, then D is a metric. Okay, here also D is a metric on C closed interval 0 to 1. It is a metric on C closed interval 0 to 1, and therefore this metric in this case is called as a Chebyshev metric. Okay, and is called, this metric is called Chebyshev, T-E-H-E-B-Y-S-H-E-V, Chebyshev metric. Chebyshev was a Russian mathematician, so name is given after him as a Chebyshev metric, or it is also called as a supremum metric. Okay, it is also called as a supremum metric. So like such, we have this 6th one, illustrative example. The next one, last illustrative example, is the example number 7. So if we consider capital C as the set of all complex numbers, if C is the set of all complex numbers and D is defined as D of x comma y is equal to the D of x comma y is defined as its one value is mod x plus mod y, and this is if x is not equal to y, and D of x comma y, its another value is 0, and this is if x is equal to y. So if D function is defined in such a way, then this D function is a metric on x. Okay, so then D is a metric on x, but here x is nothing but it is the set of all complex numbers. So therefore D is a metric on capital C, and hence this set of all complex numbers C along with the metric D is a metric space. This is a metric space. So like such, we have seen some illustrative examples. So in the last 2 classes we have studied 7 illustrative examples, and these are sufficient for clarifying the concept of metric and metric spaces. So with this we'll stop here and we'll continue in the next class. In the next class we'll solve some examples on metric spaces, in which we'll check whether the given set forms a metric space under the given function or not. Till then we'll stop here. Thank you.